Thank you, Arvind. So first I want to thank all of the organizers for organizing this program. I know that the work that is behind, and also thank you for inviting me. So my talk is about last passage percolation in the strip. There are some recent results about the model of last passage percolation in the strip. Unfortunately, I cannot stay for next week, and I think that this week was designed mostly for introductory courses. So I will try to give a talk that is rather introductory, and for that reason, I will actually mostly talk about the most standard setting of last passage percolation, and only towards the end of my talk, I will state some more recent results about last passage percolation in a strip. So the model of last passage percolation is one of the most studied exactly solvable models in probability. And its solvability is related to symmetric function theory, and specifically the Schur functions. So I'll start with that, with properties of Schur functions. And then we'll see how last passage percolation naturally arises when one looks at these properties of Schur functions. So the Schur function can be seen as polynomials. So I have variables x1 to xn. And the Schur functions are generally denoted as lambda of x. Lambda is an integer partition, so it's a non-increasing sequences of non-negative integers, lambda 1 greater than lambda 2, etc., up to, say, lambda n. And S lambda of x can be defined as a ratio of two determinants. So on top, I have the determinant of the xi to the power lambda j plus n minus j. And on the denominator, I have a very well-known determinant. This is the van der Monde determinant. So it's known that the denominator, it's just the product over all I less than j of xi minus xj. It's the simplest antisymmetric polynomial. And of course, the determinants, they define antisymmetric functions, antisymmetric polynomials here, but so if you have the determinant on the numerator, which is antisymmetric, you divide it by the van der Monde, it becomes symmetric, and it's a symmetric polynomial. So there are several distinguished families of symmetric polynomials that form a basis of symmetric polynomials and more generally symmetric functions, and the S lambdas are one of them. They are orthonormal with respect to some inner product, and they satisfy a number of very nice properties. The first one that I want to state is called the Cauchy summation identity. It's a summation identity, which is here. So I take one function S lambda, one Schur function evaluated in variables A1, A2 up to AN, and I multiply it by another Schur function evaluated in B1 up to Bm. So I take the product, I sum over all partitions lambda, and it turns out that the result is very simple. It factorizes, and it has this very nice factorized form. It's the product over all I and j's of 1 over 1 minus AI bj. And this product here, I'll denote it by pi AB, is just a shorthand notation, because this number here in our probabilistic application will be a normalization constant, and so I need a nice notation for it. There are many proofs of these results. There is one proof that uses some tools that were used earlier this week. Namely, it can be proven by the Binet-Cauchy identity. So the S lambda is written as some determinant, the other S lambda is another determinant, and we have this sum of determinant of a submatrix. So one has to invent the nice submatrix to consider, but then you can just apply directly the Binet-Cauchy identity. So the proof is purely linear algebraic, not too difficult. But there is a lot of math behind this identity, and we will see some of it. So that's one of the properties of the Schur functions that I want to consider. And I want to consider a second one, and then we will see the interactions between these two properties. So the second property that I want to consider is a decomposition of Schur functions into very simple monomials. To do that, to see how it works, one can use an identity which is the so-called branching rule. So we'll just take it as a fact here. If I look at S lambda in variables A1 to AN, I can decompose it So it's in particular symmetric with respect to variables a2 to an. And I can decompose it in the basis given by the S mu's of a2 to an. And the coefficients that will arise are called skew show functions. They are denoted S lambda over mu of a1. So S lambda of n variables decomposes as a sum over mu of the skew show function S lambda over mu times S mu of the remaining variables. And the skew show function, evaluated in here just one variable, S lambda over mu of A, is something very simple. It's just A to the power, the size of lambda minus the size of mu, and by size of lambda, I mean the sum of the parts, the sum of the lambda i's. So it's A to the sum of the lambda i's minus sum of the mu i's. And multiplied by some indicator function, the indicator function that mu interlaces with lambda, and here the interlacing is a little bit like the minors of the eigenvalues of matrices. So it's a condition that says that lambda 1 is larger than mu 1, which is larger than lambda 2, larger than mu 2, etc. So this is what I mean by interlacing, and I denoted it like that. Mu interlaces with lambda. So that defines my skew show function. Now, the identity which is on the top of the slide, this branching rule, I can iterate it. I can reapply the branching rule to S mu of A2 to AN to get some skew show function S mu over something of A2 times something remaining and apply it again. If I do that n times, what I will get is this kind of expansion. My show function S lambda of x can be expanded into monomials. So the sum is indexed by a sequence lambda superscript 1, etc., up to lambda superscript n of interlaced partitions. And what I sum is a simple monomial, xi power the size of lambda I minus the size of lambda I minus 1. So that's sometimes called the combinatorial formula for show functions. So we have two properties. A summation identity, the Cauchy identity, and this expansion into monomials. And now I want to assemble the two. And we'll do probability with that. So what I want to do, here I rewrote my Cauchy summation identity. And I want to do, to better understand this identity, is to sort of find another proof, or to better understand what is on each side of the identity, and I want to expand in monomials each side. So let's start with the left-hand side. So the left-hand side, we know how to expand each show function S lambda. So one function S lambda will be expanded using one sequence of interlaced partition, lambda 1 up to lambda n, where lambda n equals lambda. The other show function S lambda will be expanded using another sequence of interlaced partition, denoted by mu1 to mu m, where mu m is also equal to lambda. And so in the left-hand side, naturally, we'll have a sum over two sequences of interlaced partitions that end at lambda. And, well, if I get the left-hand side of this inequality can be written like that. So a sum over two sequences of interlaced partitions, and then I have simple monomials. So this is how we expand into monomials the left-hand side. Okay, now the right-hand side. So the right-hand side is a product of something quite simple. This something quite simple, 1 over 1 minus aibj. So you know that if the modulus of aibj is less than 1, you can expand it in power series like that. It's the sum over, so I want to index the sum by w between 0 and infinity of aibj to the power w. So I can plug this into this product. So here it's convenient inside the product over I and j to call this summation index wij. And then I can exchange the summation and the product. When I exchange the summation of the product, I need an index wij for each element in the product. So in the end, what I need is for all ij, I need some integers. So that's a matrix. It's a matrix of size n by m filled with non-negative integers. So I denote it by capital W. This is the matrix of the wij's, which are integers in a matrix of size n by m. And then I sum over matrices and I take the products of these simple monomials. So that's how one expands the right-hand side. So since there is an equality between the left-hand side and the right-hand side, there must be a way to match the monomials. Actually, there are several ways to match the monomials. It's not unique, but this has been studied in much details, and there are indeed some bijections between sequences of interlaced partitions ending at the same partition lambda and matrices of size n by m filled with non-negative integers. One of those bijections is called the Robinson-Chesney-Knuth correspondence. And for the moment, I don't want to tell you exactly what is the correspondence between the matrix W and the matrix lambda. We will just use the fact that there is such a bijection. And we will use this bijection as a change of variable to get something interesting in probability. So in order to relate to some probabilistic model, I need to tell you a little more about this Robinson-Chesney-Knuth correspondence. And the only one property that I need for the moment is that under this bijection, certain parts of the interlaced sequences have a very nice combinatorial interpretation in terms of the entries of the matrix W. So in particular, if I look at the partition lambda, and I look at the largest part of lambda, so lambda 1, this has a very nice expression in terms of the entries of the matrix, and the expression is the following. So lambda 1 equal to G and M, where G and M is a certain functional of the entries in my matrix. So here, my matrix Wij, I view it as decorating a n by m grid. So on the vertex ij of my grid, I put my entry Wij, and then I look at paths in the grid going from coordinate 1, 1 to coordinate nm. I look at paths which are progressing to the right and up, so upright paths. And for each path, I will consider the sum of the Wij's along the path. And I take the maximum over all possible paths of the sums. So I define G and M as the maximum over all paths of the sum of the Wij's along the path. This is generally called the last passage time. Yeah, that's how I define G and M. And the result that I want to use is that under this RSK bijection, lambda 1, the largest part of the partition, is exactly equal to G and M, where G and M is defined using the weights in the matrix. So it's a purely deterministic thing for the moment. But now one can do probability with this. So now we will assume that my Wij's are random variables, and they're distributed as geometric variables with parameter AI, Bj, where AI and Bj are the same as before, and independent. So this means that the probability distribution of my matrix W is given by a big product over I and product over J, because my entries are independent. And then I have the AI Bj to the power Wij times some normalization factor. So these terms are exactly the monomials that were appearing in my monomial expansion of the right-hand side of my Cauchy identity. And so the probability now that G and M is less than something, I call it R, this will be the sum over all possible matrices for which G and M is less than R of this probability here. But then I can use my change of variable, my Robinson-Chesney-Knuth correspondence, and instead of summing over W's, I can sum over sequences of partitions. Now the indicator function, it becomes the indicator function that lambda 1 is less than r, because we have an equality between GNM and lambda 1 in that correspondence. And I have a product of the AI to the size of lambda I minus size of lambda I minus 1, and same for J. Well, you cannot see what is here, but we have the monomials here that were appearing in the left-hand side of the Cauchy identity. And now here, in this summation here, I care only about lambda 1. I can sum over all of the intermediate lambda i's and mu i's. And what I would get, I don't have space anymore on this board, but what I would get is just the sum over lambda, the indicator function that lambda 1 is less than r times s lambda of a1 to an, s lambda of b1 to bm. So I can see, and there is a normalization factor. So here in the P of W, I had a product of 1 minus AIBJ. And this product of 1 minus AIBJ, I can see it as 1 over pi AB. Okay, so that's how one can study last passage times in percolation. So the identity that I wrote on the board is equivalent to saying that I can define some probability measures on random partitions. Probability of lambda is 1 over pi times f lambda of A, s lambda of B. And under these probability measures, lambda 1 has the same law as GNM, my last passage percolation time. It turns out that this correspondence between last passage percolation and show functions is very useful because show functions are determinants. So it implies that there are determinantal point processes in the background that allow to study very efficiently using techniques from random matrices the distribution of GNM and its asymptotics. In particular, it was proven by Johansson in 2001 that as n and m go to infinity, the fluctuations of GNM are on the scale n to the 1/3, and they converge to the Tracy-Widom GUE distribution arising in random matrix theory, that it governs the fluctuations of largest eigenvalues of Hermitian random matrices. Okay, so here I have not really explained what is the Robinson-Schneider-Knudsen correspondence. And generally in my talks, I don't explain it. But I think that today I want to tell you a little bit about what is more precisely this Robinson-Schneider-Knudsen correspondence. And I will do that through Pitman transforms, which turn out to be related to other things that we have seen this week. So the Pitman transform originates really in probability theory. So in 1975, Pitman was studying transformations of the Brownian motion. So imagine that xt is a Brownian motion. So starting from 0, so something, the graph is something like that. This is my Brownian motion xt. And then he considers m of t the supremum of x, no, there is a typo here. M of t is the supremum of xs for s in 0t. So it's the supremum up to time t. And he considers twice mt minus xt. So this is a certain transform. And he showed that this 2mt minus xt has a very nice distribution. So it's called the Bessel process. And it can be viewed as a Brownian motion that is conditioned to stay positive, to stay above the horizontal line for all t in R+. That's one way of stating the Pitman transform. So here I will not talk so much about Brownian motions and Brownian motions conditioned to be positive, but I want to focus on this transformation twice the maximum minus x, which is called the Pitman transform. There is another way to reformulate it, which I will use. So instead of this twice the maximum minus x being a transform of a single path, actually I should see that as a transform of two functions. So if I have two functions from R plus to R, let's say continuous, I can define two operations, f1 times f2 and f1 dot f2, as given by this. There is some infimum for the first one and some supremum for the first one. So I consider the increment of f1 between 0 and s, and the increment of f2 between s and t, and I take either the infimum or the supremum, and it defines new functions. So those are sort of convolution products, but using infimums or supremums. Then the Pitman transform of two functions f1, f2 can be defined like that. So P2, the 2 means that I have two functions. P2 of f is given by f2 dot f1 and f1 times f2.
Sorry, just to clarify, the arguments inside both these functions, both these definitions are the same?
Yes.
Okay. It's not f2 of t in the second one. I mean, it's not, okay.
Yeah, yes. Here what is inside is the same. The difference is infimum, supremum. I think it should be correct. But then in my Pitman transform, I have f1, f2, and f2, f1. And there is a way to reformulate Pitman's result as saying that now I take a Brownian motion in R2. So it means a collection of two Brownian motions B1, B2. Then its Pitman transform, P2B, is again a collection of two functions that I can see in R2. And it has the distribution of a Brownian motion conditioned to stay in what I call the Weil chamber. So it's the set of points x1, x2 in R2, which are ordered, x1 larger than x2. Okay, so I introduced this f1 and f2, these operations in order to generalize. Before I generalize, I want to make a connection between the Pitman transform and box-ball systems.
So your reformulation, it's how is it equivalent to the first construction?
Yes, I wanted to say that actually. So if you take this theorem and you consider x equal b1 minus b2, and you use the definition, then you would recover the first theorem by observing that if I have a Brownian motion conditioned to stay in the Weil chamber, the difference of its two components is precisely a Bessel process. But there is an equivalence between Pitman's theorem and this theorem. It's just that the process x above corresponds here to the difference of the two components of the original Brownian motion and of its Pitman transform. And the sum of the two components is something which is trivial. So here we start from a Brownian motion, B1, B2. And if I sum the two components of the Pitman transform, so it turns out that f2 dot f1 plus f1 cross f2, this is just f1 plus f2. So the Pitman transform does not transform the sum, but it transforms the difference. So this Pitman transform is, but you will see why I want to introduce this soon. The Pitman transform is also related to box-ball systems. So I believe that this was discovered by Croydon, Kato, Sasada, and Sugimoto. And actually it's related to how Pitman's theorem was proved originally. What Pitman did in his first paper on this result is that he considered simple random walks, progressing with steps +1, -1. He proved a discrete version of Pitman's theorem, and then he took a scaling limit. That's how he did. So now when you have a trajectory, a random walk with plus or minus steps, you can say that whenever you do a plus step, you put no particle on the line, and whenever you have a minus step, you put a particle. So a trajectory gives you a state of particles on Z plus. And then it turns out that applying one discrete Pitman transform, so taking twice the maximum of xs minus xt, is equivalent to evolving your particle configuration using the box-ball system. So I I hope I evolved it correctly. I'm not a specialist of box-ball systems, but you can see the details in this paper. So the Pitman transform is also connected to box-ball systems. So now that was just an aside. Now I want to explain why I wanted to introduce these two operations on two functions F1, F2. This is because it's the right setting to generalize the Pitman transform and to connect it to Robinson-Smith-Knud's correspondence. So now I will take a function with n components, f equal f1 to fn, and I denote by pi of f the Pitman transform that acts only on the components I and I plus 1. So we know how to act on two components, and now pi is the Pitman transform that acts on components I plus 1 as before. So this here is consistent with my definition before. And now, using this elementary thing, I can define a Pitman transform for functions with n components. So to do that, I have to do some sort of sorting algorithm. So what I need, the intuition is that given two functions, so I could take any functions, I could take a sine function and something like that. If I apply the Pitman transform, what I will get is, so now it will not be really exact, but I will have two ordered functions. So something maybe like that and something like that. Here I invented. You can put it on the computer and check, but you get a picture like that. So the Pitman transform should be interpreted as sorting. Pi sorts the I and I plus 1 coordinate. Now if I want to do it with n functions, I need to apply a sorting algorithm. So if I want to formalize that idea, I take the reverse permutation, n minus 1, etc. up to 1. I need to find a factorization into transpositions of this permutation. So I denote by Si the transposition I plus 1. I factorize my reverse permutation like that. And then my Pitman transform will be given by the product of Pitman transform acting on coordinate I plus 1 with the same order as how I factorize my reverse permutations.
Sorry, so then Pn depends on the order, or is the claim that it's independent?
No, the miracle, and that was proven by Bian, Bougerolles, and O'Connell, is that this definition here does not depend on the order as long as you have chosen a reduced decomposition of the longest element. And so I say longest element because this generalizes to Coxeter groups and yes. So why it does not depend? It is because the PIs, they satisfy braid relations. So Pi and Pj, where I and j are far apart, they commute. And for I and I plus 1, Pi and Pi plus 1, they satisfy some braid relation, and this ensures that this definition will not depend on the reduced decomposition. And now there is a very nice result that, which is the generalization of Pitman's theorem. If you take a Brownian motion with n components, B1 to Bn, then its Pitman transform is a Brownian motion which is conditioned to stay in the Weil chamber, being the points in Rn, that are ordered. And this last stochastic process is quite interesting. It corresponds to the process of eigenvalues of Hermitian matrix whose entries are Brownian motions. It's called the Dyson Brownian motion. And it's also a very well studied stochastic process for its random matrix applications. Okay, so why I did all that? Because now I can relate those discrete Pitman transform to RSK. So at the very beginning, I used RSK to study last passage percolation, and I didn't tell you what was the RSK correspondence. I just asked you to believe that lambda 1 is some last passage percolation time. So again, I will do no proofs, and I will ask you to believe things, but one can describe completely this Robinson-Smith-Knud correspondence using Pitman transforms. So here on the top of this slide, I've just copied again my grid m by m, the definition of my last passage time, and I will introduce some functions, or I of m will be the sum of the weights along along columns. So I define Ri partial sums of the weights along columns. And then when I have discrete functions, like those Ri's, I can again define discrete operations times and dot, a little bit as before, except that here I have a j minus 1, but that's just the detail. And then using those discrete elementary Pitman transform, I can define, as I did before, a generalized Pitman transform that acts on n components. So it means that with these functions Ri, I have functions R1, R2, up to Rn, I can apply a Pitman transform to them. And it turns out that if you look precisely what is the Pitman transform, if you look at only the first component, there is only supremums that are involved or maximums that are involved. And you can show that the first component of the Pitman transform will correspond to this maximum here. And so it's, by definition, my G Mn or Nm. And there is something more general. So more generally, the full RSK correspondence, which was a bijection between sequences of interlaced partitions and my matrix Wij, can be fully written in terms of those discrete Pitman transforms. So there is one case that we have just seen. So the partition lambda, its largest component, lambda 1, is the same as lambda 1n, which is the same as mu 1m. And this one, I already said that it was equal to GNM under the RSK correspondence, and that is the first component in my Pitman transform. But this generalizes. I can take any partition in my sequence of interlaced partition mu j, and this is equal to the Pitman transform, which can be seen as a partition at time j. Anyway, there is a full correspondence between the Pitman transform and the RSK and the sequences of interlaced partitions in RSK. So here I explained it for mu j. If I want to get the lambda i's, I need to take the transpose of the matrix W. If I transpose the matrix W, the lambda j's and the mu j's are exchanged. And so yeah, that's one way of defining the RSK correspondence. Of course, so generally the RSK correspondence is introduced as a procedure of insertion of integers into a semi-standard Young tableau. And in order to really work with the RSK correspondence, one has to use at some point this definition, but I wanted to say, to give at least one way of describing it. Okay, so now I want to talk about variations of the Pitman of the last passage percolation problem. And so what I've explained so far was understood before 2000, a few years before 2000, or around 2000. And around that time, really soon after, people looked at variants of the model of last passage percolation. So one very natural thing to look, for instance, is assume that the matrix W of weights is symmetric, Wij equal Wji. And then it turns out that one can play exactly the same game using RSK. So there are other summation identities satisfied by Schur functions, which allow to do exactly the same thing. So instead of the Cauchy summation identity, one uses something called the Littlewood summation identity, but then everything works the same. One has to choose a slightly different distribution. Wij become a geometric variable of parameter AI, Aj, and on the diagonal, Wii is a geometric variable of parameter CAI, where C is an extra parameter that controls the weight on the diagonal. And then Bike and Rains in 2003, they proved that with the same method, one can study the distribution of the last passage percolation time, defined exactly as before, in terms of a summation of Schur functions, but then I have only one Schur function, which is multiplied by some coefficient that depend on C, C to the lambda 1 minus lambda 2, plus lambda 3 minus lambda 4, etc. Again, this allows to do asymptotics, and Bike and Rains did it, and they showed that this last passage percolation time in the symmetrized environment, it converges to variants of the Tracy-Widom GUE distribution, namely related to symplectic matrices, the symplectic ensemble and the Gaussian orthogonal ensemble. It depends, the result depends on the value of C here, and there is an interesting phase diagram.
So what are you assuming about the variables AI? So are you assuming they're...
Or you
constant or?
You mean for this result or
Yeah,
for here?
or this and the other asymptotic. I mean, the size of the A's is growing, right?
Yes, so you can, for instance, you can fix AI all equal to some A,
Okay.
and take some A between 0 and 1,
Okay.
and then...
That's the kind of, I mean,
Yeah,
you
that's the
don't
kind-
consider A's different. I mean,
there are also results when the A's are slightly different, if the A's are periodic, or if the A's are actually distributed according to some distribution. There are some results. So typically the formulas, they hold for any set of variables, but then for the asymptotics, it's simpler to assume that they're all the same.
Yeah.
So in this paper of Bike and Rains that I was mentioning, so they did this symmetry class, assuming that the matrix is symmetric, but in the same paper, they also work out other possible symmetries. So you may assume that your matrix is symmetric with respect to the other diagonal. Again, you can write the distribution of the last passage time in terms of show functions, and one can do asymptotics, and they did it. You can assume also that the weight matrix is symmetric with respect to both diagonals. Again, one can do everything. They also consider the case where the matrix is symmetric with respect to the composition of these two reflections. So that is a symmetry with respect to a point. And again, one can write everything in terms of show functions and do asymptotics. So all of those cases, in all of those cases, we get sum of show functions which also have interpretations as averages over classical group. So the case of the most standard case of last passage percolation corresponds to an average over the unitary group. And then in these other cases, you get other compact classical groups. Okay, one can play with symmetries. There are, however, cases which are open. For instance, one can imagine many things, but what I want to talk about is what happens when you have two symmetry axes like that which are parallel. Then it's not known what is the image by the RSK correspondence and how to relate this with show functions.
I don't understand what symmetry about two parallel axes means what?
So here...
What is symmetric about, I mean, which two entries are symmetric, are equal?
Here I assume that I have two symmetry axes.
Yeah,
so that my entries on both sides of this one will be symmetric, and also on both sides of this one will be symmetric. And actually, as a result, it should be periodic. So if I had a narrow band, then it would be periodic. Okay. But it's a good point. So actually here, instead of assuming that I have a symmetric matrix, since I'm taking a maximum over pass, I can very well just restrict my maximum over pass and assume that my path stays between the two red lines. Because if the path was going somewhere else, because the weights are symmetric, the sum of the weights along that path would be the same as for some path that is inside. So the problem is equivalent to assuming that I'm looking at the last passage percolation time, but where paths are constrained to stay between two walls. That's the problem. And in the remaining time...
Are you assuming that your two walls are symmetric with respect to y equals x, or not necessarily?
We are assuming this. So they are parallel to the diagonal. In principle, it should not matter in terms of asymptotics. The result should be similar if we have another angle, but this is far from being very well understood yet.
But not just the angle, but the distance with respect to the first bisector, should they be equal, or?
Oh, here?
Yeah.
Here I took my picture here is symmetric. It does not really matter if my picture is not symmetric, because now I want to replace this picture by this one. And here in this picture, I don't know where is the first bisector, and it does not really matter. So now the setting is this one. It should depend on capital N parameters, where capital N is the size of the strip. And two parameters for the boundary, C1 and C2. And I take my weights to be geometric of parameter AI, AJ. Now AI, AJ are understood modulo N. And on the left boundary, WII is geometric of parameter C1, AI. On the right boundary, weights are geometric of parameter C2 times AJ. So I have two boundary parameters and bulk parameters. Now, earlier, I was defining last passage percolation times as maximum of a path that starts from a corner and that arrives somewhere. I want to slightly generalize the problem by assuming that the paths that start from somewhere on the bottom row, coordinate I0, and at I0, I start, the last passage percolation time is already something, given by some function G0 of I. So I start with some initial distribution of my last passage times on the first row. And then, knowing this and knowing the weights above, I construct my last passage time GNM as the maximum over all possible starting points I and all paths from I0 to NM, and I add the initial value and the sum of the weights along the path. So that's the model. And much is open about this model. So what is conjectured is that there is an interesting phase diagram that occurs. The richest is when capital N, the size of the lattice, is taken proportional to little n to the power 2/3. And then I look at last passage time G and N. And depending on the values of the boundary parameters C1 and C2, so for some values of the boundary parameters, the geodesic path, so the path that maximizes the sum of the weights, the geodesic path in one case will be close to the left boundary in that region. In this region, it will be very close to the left boundary. And there is a case which is more disordered here in this region where C1 and C2 are not too large. The paths, they will really wander around everywhere in the strip. And we get asymptotics which are on the scale n to the 1/3 and fluctuates according to some distribution, which for the moment is unknown. And finding it is an important open problem, which is related to Kardar-Parisi-Zeng universality class with boundaries. So we cannot solve at all this problem yet. But when we have an exactly solvable model, often the first step in order to understand the model and to have probabilistic results is to understand its stationary measure. So this is what I will talk about, and the problem of stationary measures is now solved. So first I have to explain a bit what is a stationary measure. So now I imagine that I have my strip, and I will look at the last passage times along a row. I view the height as time. So here I'm at time t, and in the next row I'm at time t plus 1, and I have a Markov process that evolves the set of passage times on a row to the next row to the next row, etc. So this Markov process does not have a stationary distribution simply because we are keeping adding weights. So the passage times on a given row, as t goes to infinity, it will just increase to infinity. It will not reach a stationary distribution. However, what we can do is to consider the difference between the last passage time here at g t plus I t and here, g t t. And we look at the increments of last passage times here and there. We look at the difference. And the set of the differences, as I varies, this actually will reach a stationary distribution. So the problem now is to find a distribution on the initial distribution G0, such that for every later time t, my increments, I denote them by GTI. So GTI are really these increments, the difference of last passage time here minus here. This has the same distribution as my initial distribution G0. This is called then a stationary measure. So for models connected to this last passage percolation model, namely the asymmetric simple exclusion process, there is a well-known technique that was introduced in the 90s called the matrix product ansatz. It is extremely powerful. It works very well for particle systems. Here, it's a little bit more complicated to apply because the state space of our Markov process is z to the n, or z plus to the n. And in order to apply the matrix product ansatz that I won't define in this talk, I will need to have a lot of matrices satisfying some commutation relations. However, last passage percolation is also very closely connected to Schur functions. And it turns out that one can exploit Schur functions and its disconnection to compute the stationary measure. And this is what I will say in the remaining few minutes.
But you say it's complicated, the matrix product on that, but can you know it can be done in this case? It works in this case?
Yes, I know that it can be done because, so initially we did not know how to do, but we used, in a joint work with Ivan Corwin and Zhongri Yang, we used another method to compute the stationary distribution. And then the result that we obtained, we could reinterpret it as a matrix product on that by defining appropriate matrices. And one can check that those matrices that satisfy commutation relations that one would have derived if we had wanted to solve the problem first by matrix product on that. The matrices themselves are simple, but really when you write the commutation relations, there are a lot of them, and they have a form which is not super nice. So it is not clear to me if we would have arrived at the same solution if we had worked directly on the commutation relations. So I think I have just 5 minutes left, so I should at least state one result. Anyway, what I wanted to explain is more the background on last passage percolation. So one way to phrase the result is this one. For simplicity, I take the inhomogeneity parameters A1 to AN to be just equal to some A. And now, okay, the answer is quite probabilistic. So I will go through this slide slowly. So first of all, I define for R, so R is a sequence of numbers, which are integers here. I can see it as a trajectory of some random walk, if I want. And I denote by P superscript random walk of R, the probability that R is actually a random walk where increments are independent and geometric with parameter Q. So in other terms, my P of R is just a shortcut for this product here. The product of Q to the R of J minus R of J minus 1 multiplied by some normalization factor. Now, the second thing I need is the Pitman transform, R1 times R2, and this I already introduced it. It's the same as before. And now I consider a distribution on two random walks, R1 and R2. So I start with the probability of a random walk R1 with jumps that are geometric with parameter AC2, a random walk R2 with parameter AC1. And of course, the answer cannot be too simple. Typically, stationary measures of models between two boundaries have non-trivial correlations, and the answer must be a bit complicated, so it cannot just be a simple random walk. But I will put a probability distribution on R1, R2, being the probability that R2 is a geometric random walk, the probability that R1 is a geometric random walk, times something. And this reweighting factor is C1, C2, the two boundary parameters, raised to the power the value of my Pitman transform at the endpoint. That's one way of describing the stationary measure, in the sense that now if I look at the marginal R1, so I don't need to have two random walks, I need just one random walk to describe the stationary measure, and it turns out that the stationary measure of the model is just the marginal distribution of R1 here. Of course, here in this distribution, R1 and R2 are very correlated. So it's not easy to express what is the distribution of R1. I mean, if you want to do it, you need to here sum over all possible R2s. Okay, so I have almost no time left. So, yes?
Does it matter that you choose R1 instead of R2?
Yes. So, yes, R1 and R2 don't have the same distribution, and here one should choose R2, but so if you reverse space and exchange, reverse space meaning instead of looking at R1 of J, you look at R1 of N minus J, and you exchange C1 and C2. I mean, there are some symmetries in the here, and so...
So R2 would not be a stationary measure or something else?
Okay, so since I don't have time, I will not pass the next slides, and actually I will sort of answer to your question. So the way we prove this result is that we say that this R1 and R2, they come from a measure on sequence of interlaced signatures, so lambda 1, interlaced lambda 2, etc., up to lambda n. Sorry. The measure on these interlaced partitions is proportional to a product of skew Shor function S lambda over S lambda I minus 1 of the AI times some other factors depending on the boundary parameters. So it's some variant of the Shor process. And here the lambdas are not partitions, they are signatures. So by that I mean that lambda I is lambda I1, lambda I2. If you want, it's a partition with only two components, and also it's not necessarily positive. So there are some variants. It's some variant of the Shor process. And it turns out that those random walks are related to this measure, this type of Shor process, where there are two components. So lambda I1 is related to R1, lambda I2 is related to R2. And the way we prove that R1 is stationary is that we embed last passage percolation into a more general Markov chain that acts on these two components. And we show that this type of Shor process is preserved by this more general Markov chain, and that if we look at the first coordinate in our Markov chain, it is exactly the Markov chain that describes the evolution of last passage times from one row to the next row. That's how we prove it. And the proof of stationarity boils down to showing that these skew Shor functions satisfy some summation identity, namely what one needs are skew variants of the Cauchy identity and skew variants of the Littlewood identity. That's essentially how the proof goes. And the method, so here I explained the method for the model of last passage percolation and Shor functions. But it works exactly the same if we replace last passage percolation with a model known as the log gamma polymer. And then the Shor functions become what is called Whittaker functions. And the RSK correspondence become geometric RSK correspondence. The Pitman transform become geometric Pitman transform. There's, everything can be lifted to this more general setting. And it works also for other families of symmetric functions. One can consider the high Littlewood case. One can consider, so this is in progress, but one can consider partition functions of vertex models, which define symmetric functions, which typically will satisfy the identities we need. And actually, as long as we have a family of symmetric functions satisfy two types of summation identities, one can apply the method. So now I jump to the conclusion slide. So in this talk, I wanted to introduce last passage percolation. I explained how it naturally arises from the Cauchy identity and the combinatorial formula for Shor measure using RSK correspondence. I explained that RSK is actually the same thing as a generalization of the Pitman transform. And then I moved to more general, more recent results about last passage percolation in the strip, where the stationary measure can now be expressed in terms of reweighted random walks. And the key idea of the proof is to view last passage percolation as the marginal of a more general Markov chain for which a certain kind of Shor process is stationary. And I thank you for your attention.
Perhaps because we are short of time, maybe one quick question.
Yeah, so you mentioned this geometric version which involves Whittaker functions. Are the various symmetric classes that you looked at in the beginning also reflected in this formulation in terms of other type of the algebras?
Yes and no. So okay, I will not answer exactly to your question, but I make a small comment. So one could expect that when we have a matrix with no symmetries, we get the type A symmetric function, and when we have a matrix with certain symmetry, we get the type B, or with another symmetry, the type C, etc. It does not work like that. It turns out that type A is related to the matrix with no symmetry, and when you put one symmetry axis, it's related rather to the Littlewood identity for the type A functions. And this thing, which is true for Shor function, is also true for the Whittaker functions. But then there are a number of identities, and one can see some type B functions arising in some of the cases that are discussed. They are results of Zigorras, BTA, BC on this, mostly in the Schur case, but I think some of this should be true as well in the Whittaker case.
Okay, maybe one last question.
Sorry. Till you work with Schur functions, do you have an interpretation of the story in representation theory?
No, short answer. I don't know.
Okay, then let's thank the speaker again.
Thank you.